Okay, welcome to the last part. This is part 6. Welcome to the last part of the presentation on nomenclature. And I hope you have stuck with me through the other 5 presentations. I hope you got something out of them. Hope the narration really is helping to explain some of the work. I'm not quite sure how else to do it. Unable to develop the technology to do it like Khan-style Academy, where I can interact in a much more dynamic way, where I can write and explain at the same time instead of writing it first and downloading the image into a static PowerPoint, so you only see the fully worked out problem and then I have to explain it point by point. So in any case, I hope you've stuck with me. Hope you're getting something out of this. Now, in this particular last presentation, this is going to be about Chapter 7, Section 3 and 4. This actually realigns with the chapter now. So we're back with the chapter. If you haven't read the chapter at all, if you pick it up at Section 3 and read Section 3 and 4, which are kind of short, that you will find that this falls right in line with that presentation, as opposed to the previous parts where I've presented the type 1, 2, 3, and 4 naming systems and formula writing, that they don't line up with the chapter in that the chapter doesn't use the Stevens-Zumdahl method. So, you know, there's that problem. But this lines back up with the book. Okay, let's student learning map material. I'll skip over this. Student learning map material, I will also skip over this, but we will be dealing with empirical formulas and molecular formulas in this presentation. First thing we need to talk about, though, is a process and a concept called percent composition, which is not a big concept. It's something you're kind of familiar with. If you have a shirt that is a blended material, maybe it's 80% cotton and 20% synthetic material, well, that's percent composition right there. 80% one thing, 20% another. It might be interesting, actually, to take a box of Lucky Charms and find out what is the real percentage of marshmallows in Lucky Charms. So, very interesting there. How about this? Oreos, double stuffed Oreos. Are they really double stuffed? It's a percent composition discussion about the white filling in between. You know, is it really double? You know, looks double, but is it really double? Okay, so what is percent composition? Well, percent composition is, by mass, the percentage of the composition of an element in a compound is one way to do it, but any part in any whole, doesn't matter. So in the shirt, 80% cotton in the 100% shirt, 20% synthetic material in 100% of the shirt. So part in a whole, in this case, we're going to talk about element in a compound. And there's your part versus whole, element versus compound. An example to work. And I did not do very much handwriting early on, so you're just going to see the typed version of these answers, but I'll explain the way through it. So what is the percent composition of the elements in sodium carbonate? So in order to do this question, the first thing you have to be able to do is write the formula for sodium carbonate to know what elements are in it. That's the first thing. And that is your Chapter 7 earlier skill set to take this name and create a formula out of it. And that, by the way, would be a type 1 formula, because I look at this and say, oh yeah, sodium. Sodium is a metal. Sodium has only one charge, so this is a type 1 compound. Therefore, I will write the elements down, oxidation numbers, crisscross, and be done with it. Okay, so here is the formula you would develop. Positive 1, negative 2 crisscross to give you this formula of Na2CO3. Na2CO3. So with that formula, what do I have? I'm going to take sodium. The molar mass of sodium on the periodic table is 22.99 grams for every mole. So I looked that up on the periodic table for sodium under number 11. All right. I have 2 sodiums, so I'm going to double it. Then I have to look at the carbon. Well, carbon has a molar mass of 12.01 grams for every mole. It's on the periodic table. You can look it up. There's only one of them, so times 1, same mass, right? Well, with oxygen, oxygen has a molar mass of 16.00 grams for every 1 mole of it, and I have 3 oxygens. So I'm going to multiply this whole thing by 3. 16 times 3, there's where the 48 comes from. So here is each of the parts. And then you add them up, and there's the whole thing. So each of the parts, and there's the whole thing. Now what do? Well, the general formula is take the mass of the part and divide it by the mass of the whole. Now, in order to make it a percentage, we're going to have to multiply by 100. So that's what that does. That makes this a percentage. So I take sodium. Sodium in the compound is 45.98 grams. I'm going to divide it by the whole compound, 105.99 grams. You do that, the units all cancel, by the way, times 100 makes it a percentage. You do all this and it turns out that sodium carbonate is a little over, just a touch over, 43% sodium. What about the carbon? It's the same process. I simply have to substitute the part in. The whole doesn't change, but the part does. So 12.01 grams divided by the 105 number, almost 106, multiplied by 100, units all cancel, and this is only, what, about 11, just a touch over 11%. So 11%, 11.33% carbon officially. Now, how do I know 4 sig figs? Because these are all to correct significant figures. Well, 4 significant figures divided by 5 significant figures gives me 4 significant figures for my answer when I'm dividing, and the multiplication doesn't really affect it. That just turns it into a percentage. Okay, then do the oxygen. Well, 48 grams divided by 105.99 grams times 100 equals 45.29%. Now, technically, if you do all of the elements in a compound and you add up all the percentages, they should add up to 100% because this is the whole compound by percentage. So that's a nice little trick, you can kind of check your work with. But this is percent composition, and percent composition works with any part of any whole compound. Now, what can you do with percent composition? Well, there's a little bit more that you can do with it. We could use the same process, take a part, divide it by the whole, times 100 gives you a percentage. We could use the same process for determining the percentage of water in a hydrate. Okay? So check out this example. What is the percentage of water in nickel 2 sulfate dihydrate? Well, here's the formula. Nickel 2 sulfate, nickel with a 2 positive charge, sulfate with a 2 negative, they cancel, so NiSO4, dot, 2 waters. So I'm looking for the water. This is my part, but I have to do the whole thing as well. So let's move on and see what that answer looks like. Okay, so I looked at my nickel, 58.69 grams from the periodic table for a mole of it. I only have one of them, so there you are. Same thing with the sulfur, 32.07 from the periodic table, and I only have one of them. Oxygen, 16 from the periodic table, remembering that we are always rounding to the nearest 100th in all of our atomic masses when we go to the periodic table before we do anything with them. This is so we agree with what your book does. It's your book's strategy. And we talked about why that is in class before, so there you have it. Okay, so 16 times 4, because I have 4 oxygens in the compound, and that comes up to 64. Now for waters, I didn't break it down because I really want to look at the water, but you have 2 hydrogens and 1 oxygen. Hydrogen is 1.01. You got 2 of them. You got to double that. Add it to 16. That's where I get the 18.02. You certainly can't look water up on the periodic table. You look up the hydrogens and the oxygen and you add them together. But I needed them added together because I want to treat it as a unit. This is my part. I'm not looking at oxygen. I'm not looking at hydrogen. I'm looking at the water here. So 18.02, and I got 2 of them because it's a dihydrate. So there's my water groupings. Well, I add them all up. This is the whole thing. Okay, so there's the whole. And I had to include the waters in order to make sure I had the whole compound. Then I take my waters alone, so my 36 number, divide it by the whole thing, and then I can do the percentage error, or the percentage of water. So 36.04 grams, this is my water, divided by the whole compound, times 100. Turns out that this is slightly less than 19% water in this particular substance. So it works for any part of any whole. As long as you know what the whole is and what the part is, it works great. And we almost always do this by mass. There are other ways to do it with other units, but we almost always do it by mass. And in this chapter, exclusively, we do it by mass. Okay, what is an empirical formula? Well, first of all, empirical formulas are derived through experimentation of unknown substances or known substances that we want to confirm that it's actually what we think it is. So, hey, I think this is table sugar. Let's test it to make sure, and we do it chemically, not by taste. So we would develop an empirical formula from measurements in order to then start to verify if indeed this sample is glucose, simple sugar, sucrose, table sugar, or something else entirely, maybe salt, right? Okay, so empirical formula. First of all, what an empirical formula is, and I'm hoping that you read your chapter before you actually are watching this presentation, because you know my presentations always are abbreviated, not quite an outline, but certainly not very fleshed out as far as concept and skill set. So read your chapter, come back to this, and certainly I hope that this will make a lot more sense. But empirical formulas, what are they? They're the simplest whole number ratio of elements that are contained within a compound. Empirical formulas are obtained from experimental measurements that may report the percent compositions. Empirical formulas are very useful as an initial step when identifying new and unknown compounds, and this can eventually lead to finding what the actual compound's formula is. An empirical is a greatly reduced, simplified formula, not the complete molecular formula in most cases. And so it's a beginning step in experimentation to identifying known and unknown substances. Okay, so how do you do an empirical formula? I think from your book, it's broken up into like 3, 4, or 5 steps. I think I have like 4 or 5 steps. And I would, like in class, I would ask you to write the step down. I have 2 running examples I will show you at the end. Normally I would do these on the board. Here are the steps. I will give them to you each, and then I will show you how those steps look with these running examples of this silver, phosphorus, and oxygen compound for one, and this niobium and oxygen compound for a second example. And I'll go through all 5 steps for each one of these substances at the tail end of the 5 steps. Okay, so what do we do? First of all, if we are beginning with gram amounts of each element, I'm sorry, I said if. Most of the time we will begin with gram amounts of each element. If so, then step 1, that's all you got to do is just have gram amounts. If you don't have gram amounts, chances are you're going to have a percentage. If you have a percentage, no sweat. All we got to do, like these are all percentages down here. They're not grams. All you got to do is change that percentage sign to a G for gram, and it works. I mean, there's no calculation necessary. So instead of saying 77.3% silver, we could say 77.3 grams of silver, and step 1 is ready to go. How can that work? How can we just change that to a gram? Here's why. This whole compound represents 100% of it. So what if we had 100 grams of this compound? Therefore, 77.3% of that 100 grams would be silver, meaning 77.3 grams would be silver. So you can do that. So it's a nice little quick mathematical trick where the percentage can just be changed to a G for gram, and then step 1 is done and you're ready to go to step 2. Well, step 2. Step 2 is pretty simple. You take all of those elements and convert them to mole amounts. That's all you got to do. So you're going to do a gram to mole conversion, and of course you have to have a periodic chart for that. Now, once in a great while, a problem on a homework assignment or in a book will start with mole amounts. If you've started with mole amounts, step 2 is done as well. Step 1 is bypassed and step 2 is done. But most of the time you really are starting with percentages or grams, and you have to go through step 2. Okay, now step 3 is interesting. Here is step 3. Step 3 is where you're going to take all of your answers. In that running example of silver, phosphorus, and oxygen, there are 3 answers that we would have. We would have an answer for a mole amount of silver, a mole amount of phosphorus, and a mole amount of oxygen. Of the 3 numbers that you would have from that math, right, you would actually have one value that would be smaller than all of the others. So what we would do then is we would take that smallest answer and divide all of our mole answers by that smallest mole amount. Now, you take that smallest mole amount and divide it into itself, it's going to be 1. So 0.05 moles divided by 0.05 moles is 1. So one of your answers will always end up being 1. The others, well, it's going to depend. But that's what you do here. It'll be shown to you in the subsequent example when I work it out. Okay, once you have done that, step 4 is relying on your division in step 3, so you took them all and divided them, that your division will yield small whole numbers. So your answer should be really close to whole numbers. If they are less than a 0.25 away, if they're 0.2 away or less from a whole number, then you can simply just round it to a whole number because we're not worrying about sig figs at this point. Just round it to a whole number and you're almost done, because that whole number will represent the number of atoms in that compound of that element, and you can then assemble a formula from it. But once in a while, these numbers will not be close to whole numbers when you do the division. So if you divide your numbers and you come up and it's like 0.45. Well, 0.45 is too far away from a whole number in this case to round it just to a whole number. It's just too much. So what I would do is I would say, well, 0.45, that is super close to 0.5, right? And that's halfway there. So if I doubled that, that would create a whole number out of it. And so you would look to double or triple most values. Rarely would you have to quadruple something, but you can't do anything more than that. Because if you have to do more than quadruple it, you're probably that close to a whole number, and you just round to a whole number. So you may have to double, triple, or quadruple. Now, whatever you do to one thing, you have to do it to everything in the substance. So in that question where I had the silver, the phosphorus, and the oxygen, if one of those values had to be doubled to make it a whole number, you'd have to double them all. But if the other two are close to a whole number anyway, doubling them still makes them a whole number. So that's, that doesn't change anything. But it does affect the ratio, and that's the important part here. So hopefully in step 4, you get the whole numbers automatically. If you don't, double everything or triple everything or quadruple everything, and you will get the whole numbers at that point, close enough to round it and be done. Then do in step 5 is you can simply then use those whole numbers to create subscript for each of the elements in the compound, and that gives you the empirical formula. Now, many times this will not be the final formula. Remember, this is just a piece of the puzzle. It's not the final end puzzle. So, it's just the smallest whole number ratio of elements in that compound. Okay, now let's see that running example with the silver and the phosphorus and the oxygen all worked out. Now, I don't have it stepwise, like on 5 or 6 slides. I have it all at once, but let's explain it here really quick. Okay, so here we go. Here's my running example number 1. Here I have my 77.3% silver, my phosphorus, and my oxygen. To complete step 1, I simply changed the percentage sign to a gram, and that was it. That's entirely step 1. I kept a running example going, so I just did the whole problem here. That's why you see this crossed out, but that's because I'm doing something in step 2. But that's what I did. So there's step 1. It's literally just that easy, going from percentage to gram. It assumes a 100 gram sample, and so the percentages can be grams. Okay, in step 2, I want to convert to moles, and so that's what step 2 is. I look up the periodic table for silver. That's for every 1 mole. That's what that is. Multiply, divide, and I have an answer over here in black. Same thing for the phosphorus. Here's my mole answer in black, and my conversion for oxygen. Here's my answer in black. Okay, that's step 2. These black answers, that is step 2. What about step 3? Well, step 3 says divide by the smallest mole amount. So I have 0.7, 0.2, 0.9. The phosphorus is the smallest number. So everything gets divided by the phosphorus. So 0.7 divided by the 0.2 number. This one obviously divided by itself. The 0.95 divided by the 0.2 number again. All right, when I do this, the division yields, and notice, the units cancel, so now moles go away. There are no units of measure at this point, which is a rarity for us, but no units. So here I have 2.99 silvers. Of course, this yields exactly 1 phosphorus, and this yields 4 oxygens. It's really so super close to 4 that you round it right to 4. Well, 2.99 is easily rounded to 3. You know, that's well within that kind of 0.2 range that you're allowed to round. So this rounds to 3, and so what do I have? In step 4, they are whole numbers. 3, 1, 4, and in step 5, I simply bring them together and make these subscript. So, silvers, there are 3 of them. That should be a 3. I think that's just a really sloppy 3. It almost looks like a 7. But that's a 3. So, silvers, there are 3. So, Ag3PO4. I left the order intact by the elements that were given to me in the order they were given. The order up here at this moment doesn't matter. But, you know, that's just the order that I had. So there is a fully worked out example for example 1. If you understand that, then you may not need to do too much with example 2. But there is a thing that is different in step 4 of this next example. So you might want to at least focus on that for a moment, even if it's without the narration, right? So you can just mute me if you want. Okay, here is example 2. And example 2 had niobium and oxygen over 93% and a little at 6.5%. So step 1, percentage to gram, it was that easy. Step 2, convert to moles. I looked up niobium, which is one that I don't have memorized. I got a lot of these memorized, but niobium is just an unusual one. I just don't run into it. And so that's 1 mole of that. For oxygen, converted the 6 grams over to moles, and it's 0.4. Well, in step 2, I'm done with the black answers, right? In step 3, what I want to do is divide by the smallest. Well, up here I have 1, down here I have 0.4. So I divided both by 0.4. 1 divided by 0.4 is 2.48. 0.4 divided by 0.4 is just 1. All right, well, 2.48 is, in step 4, not close enough to a whole number in order to actually round it. So 2.48 is really close to 2.5, so I figured doubling it would get me all I needed, and doubling it gets me really to 5. But what you do to one, you gotta do to the other. So if I double this, I double the oxygens, and this then is a whole number ratio, step 4, in this case the multiplier, 4a, that this is now my whole number ratio, and then I can, in step 5, write my empirical formula, and NB5O2. That's the empirical formula, the smallest whole number ratio of niobiums to oxygens in this particular compound, based upon experimental evidence that gave us the percentages of these elements from some sort of maybe mass spectrometer, if you will. Okay, moving on. Now, how do we go from an empirical formula to a molecular formula? Well, it's actually just another step or two. So let's check. So, what is a molecular formula? Well, a molecular formula is the full and complete formula for the compound where all of the atoms are present in their right, correct, proper numbers. So for instance, check out glucose. Glucose is a simple sugar that is created in photosynthesis by plants. So it has a molecular formula of C6H12O6. Very common. Most people actually know this when they go through a science class. It seems to come up quite a bit. Now, what is the empirical formula? Well, notice 612-6 reduces down to a 1-to-1 ratio. This is a 1-to-2-to-1 ratio, and the empirical formula of glucose is a 1-to-2-to-1. So experimentally we would discover this, but we got to figure out a way to get from this empirical back to the molecular and say, oh yeah, this is indeed glucose. Or if the empirical formula doesn't get to this, it's not glucose, it's something else. Okay, so that's the difference between these two and how we want to get from one, the empirical, to the molecular. You can take molecular formulas and reduce them down to see what their empirical formulas look like, but most of the time that's not the direction we're going unless we're just practicing for empirical formulas. Let's move on. Okay, so the molecular formula mass is always a whole number multiple of the empirical formula's mass. So let's take, for example, the empirical formula of the 1-to-2-to-1 ratio CH2O. Well, CH2O has a mass of 30 grams. What if we doubled this? If you double the whole thing, you get this, C2H4O2. Notice everything is just doubled. Excuse me. If everything is doubled, it has now a mass of 60 grams for every mole. Well, what if instead we took the empirical and tripled it, C3H6O3? Now we have a mass of 90. You can see the pattern. Take the empirical, quadruple it. Take the empirical, multiply it by 5. I guess that's a pentuple. Or a septuple, I guess, for, sept for 6, but we would have said hex, right? Hexa. And notice what happens to the mass. You quadruple it, 120. If you took 30 and you multiplied it by 5, you get 150. And all of these would get 180. So notice that the molecular formula's mass is always just a multiple of the empirical formula unless the empirical formula is the final formula. It happens once in a while. And so it would be 30. You'd get there and you'd be done. The formula would be just 1 to 2 to 1 and you're done and the mass is 30. But many times it's a multiple because the molecular is different. Let's move on. Okay, so I've kept kind of this whole step 1, 2, 3, 4, 5 going, and I'm just going to call this steps 6 and 7 and 8, I think, or steps 6 and 7. So what do you want to do in order to go from the empirical to the molecular? Well, here's what I would do. Divide the molar mass of the molecular formula, so you're going to just take the molecular formula and you're going to find its mass, and divide it by the empirical formula's mass. So here's my empirical formula mass. When you do that, bigger number divided by smaller number, you're going to get a value out here. This value is going to be super close to a whole number, and it doesn't matter how close you are. You just round it to a whole number and be done with it. Okay, so that's all we need. This z value, this whole number out here, is what you want to multiply the empirical formula by to get the molecular. So you divide the big mass by the small mass, you get a number, and then you take that number and you multiply it to the formula. Don't multiply the mass, multiply the formula itself, like that whole CH2O got doubled, tripled, quadrupled, etc. Right? So that's what this says. The quotient, Z, is the value used to multiply the empirical formula to obtain the actual molecular formula. So this Z multiplies the subscript. Let's move on and see an example. Okay, I set this example up. I didn't bother to type it. I am simply just using the niobium example. So if we started with this question, a compound was found to be composed of 93.5% niobium and the remainder would be oxygen. Of course, if it's a 100% sample, the difference between 100% and this number has to be the oxygen. And that, of course, mathematically came up to 6.5%. Okay, find the empirical formula. That's the first question. Well, we already did this in a previous example, but what I would do is I'd start with my niobium and my oxygen, and I would go through the steps 1, 2, 3, 4, 5, go through all those steps and find the empirical formula NB5O2. So that's just the first part. Now, the second part of information. It was found experimentally that the molecular mass of the compound is 2,000 grams for every mole. So that would have been also done experimentally. Find the molecular formula of this compound. Remember, this 2,000 grams is the big number, and that is somehow a multiple of this mass here. So how I would find that multiplier is I could do a chart like that glucose chart where you had the CH2O and it weighed 30 and you double it, triple it, quadruple it, and you could do that. That's time consuming. That's almost like trial and error. And so I'm going to eliminate that, and I'm just going to do this here. I'm going to take the big mass given to me in the problem, 2,000 grams. I'm going to divide it by the empirical formula's mass. Now, I don't have that. I got to calculate it. So I've got to look up niobium, have 5 of them, going to look up oxygen, have 2 of them, add that together, and that's the empirical formula's mass. You divide these two, gives you a multiplier. Well, the math comes up to be 2,000 divided by 497. Because you add these 5 and 2 up, you'll get 497. 2,000 divided by almost 500 comes up to be close to 4. We're going to call it 4. That 4 is your multiplier, so I'm going to take the empirical formula, multiply it by 4. down here. Here's my 4 times, here's my empirical formula, 4 times 5, NB20. 4 times 2, 08. NB20, 08 is the molecular formula. There you go. That's how it's done. Might not make a whole lot of sense until you do a couple of them yourself, and I strongly encourage you to read the chapter because it'll give you more context and more examples. There is one more example. So let's check this out. Oh, I'm sorry. This is not a new example. This is a different way to phrase the question. So a compound was found to have the empirical formula of NB502. Okay, of course, that's from the previous slide. It was found experimentally to have the molecular mass of the compound being 2,000 grams for every mole. Find the molecular formula of this compound. Well, a question that is written this way has already completed steps 1 through 5 for you because it gives you the empirical formula. So the previous slide gave you the information to find this before you went on. This question actually sets it up to where you already know the empirical formula, so you don't do steps 1 through 5. Only picking it up at steps 6 and 7 to get that final answer. So you'll have questions like that where you only have to do these 2 steps. There are other questions where you have to go from scratch and go through the whole thing, find the molecular, then find the empirical, then to find the molecular. Okay, I have one more example, and this is, really straightforward, really quick. The molar mass of a compound is found to be 240 grams for every mole. We know the empirical formula is CH2O. So this is very much like that last example one moment ago where I know the empirical formula, I know the big mass I'm shooting for, I don't have to do steps 1 through 5 because I know the empirical formula. So the question is, what is the molecular formula for this compound? And the question, the sub-question, if you will, is this glucose, C6H12O6? All right, well, I have the big mass. I got to find the empirical mass, so I'll add that all up. I got to do some division, so let's go to the next slide. Okay, here we are. So 240 grams divided by the empirical formula's mass, 1 carbon, 2 hydrogens, 1 oxygen. Well, you add that all up, that comes up to be 30 grams. 240 divided by 30, my multiplier is 8. So I take my empirical formula down here, multiply it by 8. 8 times all the subscript, 8 times 1, C8, 8 times 2, H16, 8 times 1, 8, C8, H16O8. The molecular formula is then C8H16O8. It is a 1 to 2 to 1 ratio, so it does come from the empirical formula, so that's a match. And this is not glucose. I don't know what it is, but I do know that it's not glucose. Okay, one last slide and we're done. So, this is the end of chapter 7. This covers the entire chapter to include all that naming and formula writing where we took a different journey to learn the rules than what your book did. But again, we'll all name the same compounds and write the same formulas regardless of the path that you take, book-wise or the Stephen Zumdahl presentations. In any case, please make sure that you have attempted all homework. Ungraded homework in this chapter is just as important as graded homework. Now, if it's ungraded and you're still working on it, you can do maybe, if there are 20 compounds, maybe you pick 10 of them and do 10 of them and then check answers. And if those 10 are going okay, chances are if it's ungraded, everything's going okay. Then you go on to the graded work that matches up with that and attempt it again, that time for grade, get that submitted so I can take a look at it, get the grades in the grade book. And you can always contact me with questions. So check and make sure that you've done all the graded work. Once you are satisfied, you've gotten all of the notes, you've watched all the presentations, you understand, you have a level of mastery you are comfortable with, naming, formula writing, percent mass, empirical formula determination, molecular formula determination, those are the big skill sets, handling hydrates, back in the naming, then take the test. Certainly check with me if you have any questions along the way. I have office hours, but generally I'm available most any day. Just text me if you want me to get my attention very quickly. Otherwise, you can send an email or something like that. Okay, this is it. That's the last slide. So thank you very much, and I will see you in Chapter 8, which will be the last chapter that we'll have a chance to cover together before the end of school.